This is the last lecture on thermochemistry, and it is Kirchhoff equation. And the Kirchhoff equation actually provides a relation. The temperature dependency of heat change of a reaction. If we know the heat change of a reaction at a temperature T2, then the same could be calculated at another temperature T1. And this equation is very important whenever the effect of heat change with the temperature is required. And now I shall give a general equation, stoichiometric equation for this chemical reaction. And suppose this is nu1 A1 plus nu2 A2, and giving you this nu3 A4 and plus nu4 A4. As I have stated earlier, this A1, A2 are the reactants, A3 and A4 are the products, and nu1, nu2, nu3, nu4 are the stoichiometric coefficients of this equation. So this could be written as 0 equal to minus nu1 A1 minus nu2 A2 plus nu3 A3 and plus nu4 A4, or we can write 0 equal to summation of this nu I and AI. AI the reacting components of this, or the ith reacting components, and AI its stoichiometric coefficient. And this nu I is the negative for reactants, negative for the reactants, equal to positive for products. So the heat change at constant pressure, that we call this enthalpy change. The enthalpy change of this reaction, could also be written in this way: summation of nu I and H bar I. This H, where H I bar is the molar enthalpy of the reacting components, reacting component AI, and nu I its stoichiometric coefficient. It means that if we elaborate like this one, then minus nu1 H1 bar for the reactant, minus nu2 H2 bar, and plus nu3 H3 bar, and plus nu4 H4 bar. H1 bar, H2 bar, H3 bar, H4 bar, these are the molar enthalpy of this A1, A2, A3, A4. And stoichiometric coefficients according to this rule, negative for these reactants and positive for the products. And as we like to determine or like to find a relation of the how this delta H will be affected by this temperature, or how this delta H will vary with temperature, we shall have to differentiate this one with respect to T at constant pressure. So whenever this could be done, we can write del H by del T at a constant pressure, left hand side, and here minus nu 1, and it is del H1 bar by del T at a constant pressure, and minus nu 2 H nu 2 and del H2 bar divided by del T at constant pressure, and plus nu 3 stoichiometric coefficient of A3, and del H3 bar by del T plus nu 4 and del H4 bar by del T at a constant pressure. And we know this del H by del P, del H by del T at constant pressure equal to Cp. Cp means it is molar heat capacity at a constant pressure, at a constant P. So if we replace this one, then it will be like that, minus nu 1 and Cp1 minus nu 2 and Cp2 and plus nu 3 and Cp3 and plus nu 4 and Cp4. Cp1, Cp2, Cp3, Cp4, these are the constant pressure molar heat capacities of A1, A2, A3, A4. And this could be written also like this way, actually nu 3 and Cp3 plus nu 4 and Cp4 and minus nu 1 Cp1 and plus nu 2 Cp2. And this one also could be written as a summation of nu I and Cpi. So this is the molar heat capacities of the products, means nu I and Cpi of the products, and minus summation of nu I and Cpi for this reactants. So this one equal to del Cp. It is the difference of the constant pressure molar heat capacities of the product and the reactants, and this is delta Cp. So in this delta Cp, we can write, instead of this one, this one equal to del Cp, where Cp is the difference of constant pressure molar heat capacities of the products and reactants. reactants. And this is the differential form of this Kirchhoff equation. It is the temperature coefficient of this heat change at constant pressure equal to this density. Now actually, if we consider the heat of reaction at a constant volume, then this relation will be a del U divided by a del T at a constant volume, and this one will be equal to del Cv, and it is similarly difference of constant volume molar heat capacities of these products and reactants. And this del Cp, we can write again this one equal to summation of mu I and Cp I. If the standard states are considered, if the reaction is at standard states, then heat change will also be at the standard states. And in this case, in all the terms, zero superscript to be added up. And now this situation becomes like that. Del Cp, if we like to get this integrated form of these two, then it will be integration del H, here del H1 and del H2, and this is equal to integration del Cp and dt and temperature T1 and T2. Del H1 is the enthalpy change of this reaction at this temperature T1. Delta H2 is the enthalpy change of the same reaction at this temperature T2, and del Cp is the difference of constant pressure molar heat capacities of the products and reactants. And similarly, this one will be also this D and del U, del U1 and del U2, and this is integration, and del Cv into dt, here T1 and T2, T1, T2. So this would be written as again I shall write this del Cp equal to summation of mu I and Cp. The left hand side, this after the integration delta H2 minus delta H1, and this one equal to T1, T2 and del Cp and dt. In this case also similarly like this one, and del U2 minus del U1 equal to T1 and T2 and here del Cv dt. Now actually this one would be integrated if we know this del Cp, how this del Cp depends on temperature. So these two cases may arise. One is the case 1, when suppose the temperature range of the or temperature range is not very high, then actually a dependency of of del Cp with temperature may be ignored. And del Cp is assumed to be independent of temperature, independent of T. In this case, the situation becomes very simple, and del H2, that means enthalpy change of this reaction at this temperature T2 equal to same at the temperature T1, and this one plus del Cp and T2 minus T1, and this is the equation number 1. And in this case also, this del U2 equal to del U1 and plus del Cp T2 minus T1. In this case also, this one is assumed to be temperature independent. But it becomes more complicated in case 2. Case 2, del Cp when depends on temperature. Depends on temperature T. So these calculations, this integration, we could only do if we know how this del Cp depends on temperature. Find a relation. We should have relations of this del Cp with this temperature. If the relation is not known to us, then we can find this relation in a practical fashion. Suppose Cpi, molar heat capacity at constant pressure of this Ai component, we can write Ai plus Bi T plus Ci T square and plus dot. And this one is called the value of Cpi is expressed or related with this T as power series of T, or it is called the virial equation. As we do not know the exact relations of the Cp with T. In this case, this A1, Ai, Bi, Ci, etc. are called virial coefficient. Of the reacting component Ai, and these are characteristic constant of this reacting component Ai, and this is a converging series. This is a converging series. Converging series means this Bi, this virial coefficient is 1,000 times less than Ai, and again Ci is 1,000 times less than Bi. So whenever the extreme accuracy is not required, then we can limit this equation up to this one, and it is generally used. Ai and Bi, these are the virial coefficients of Ai and this one is very small, and the other terms also again smaller and smaller. Or if we like to have this more accurate value, accurate relations of this CPI with the temperature, then this equation, this term would also be included. And the values AI, BI or CI, they are of this reacting components AI are determined by means of experiments. And suppose at this temperature, suppose up to this extent, this relation, I like to keep a limit. So this at this temperature, suppose and suppose for A1, first reacting components, then actually at temperature T dash, this relation is suppose CP1 dash and plus A1 dash plus B1 T dash A1 B1, these are the virial coefficients of this first component A1, and at this temperature T dash, suppose this Cp value of this first component is Cp dash, and Cp dash would be determined by means of experiment at the temperature T dash keeping in a thermostat. And at suppose another temperature T double dash, this becomes a Cp1 double dash equal to A1 plus B1 and T double dash. A1 and B1, they are the temperature independent, and at this another temperature, this Cp1 value is also calculated, and it is a Cp1 T double prime. So this is equation number 1 and this is equation number 2. And from these two equations, by solving, we can get this A1 and B1. So once this A1, B1 is known, similarly for A2, A3, A4, all are to be determined and have to be given here. So then we can get an exact relation between CPI with the T. If we like to include this term, evaluate this term Ci, then another temperature, this CP1 triple prime equal to A1 plus B1 and T triple prime, another third equation is required to calculate these three unknown quantities. So for every substance, these virial coefficients have a particular value. Now this is del Cp, del Cpi, this del Cpi, del Cpi equal to, it is mu I, or del Cp of this reaction is equal to mu I and Cpi. So in this case, it will be this summation of, putting this value here, summation of mu I, Ai. Mu I is the stoichiometric coefficients of this reacting component Ai, and it is the virial coefficient of that component, and plus summation of mu I, and instead of Cpi we can write here then Bi, and this is taken in a bracket and it is T. We are limiting these relations of these two terms. then this one could be written as alpha plus beta T. Alpha is temperature independent terms and beta T, this term is temperature dependent. So these relations now we have developed and we can put here. So del H2 equal to del H1 and plus integration T1 T2, and here instead of del Cp we can write alpha plus beta T plus dot and dt, or del H2 equal to del H1 and plus alpha T2 minus T1 and plus beta by 2 by integration and putting this limit, and T2 square minus T1 square and plus dot. If we would keep this gamma, then it will be gamma by 3 and T2 to the power 3 minus T1 to the power 3 and so on. So this is the exact relation of this effect of temperature on this enthalpy change of this reaction, and beta, whereas del Cp depends on temperature, alpha, beta, they are determined by means of experimental way. And similarly, if we consider this one, then it will be also heat change at constant volume. Then U del U2 equal to del U1 plus, suppose it is alpha dash, and T2 minus T1 and plus beta dash by 2 into T2 square minus T1 square, and here it will be this gamma dash and 3 and T2 3 minus T1 3 plus dot. So this is the effect, this is the relation, this is the Kirchhoff equation which relates the enthalpy change or internal energy change of a reaction with the temperature. If we know this value, this one, and T1 and T2 and alpha, beta both are known for this reaction, then delta H2 could be determined. I shall put some important two problems to illustrate this one. So, now I shall formulate two equations for this Kirchhoff's, two forms of this Kirchhoff's equation. One is case 1, when del Cp is assumed to be independent of T. In that case, del H2, this is the enthalpy change at this temperature T2, and del H1, it is the enthalpy change for this T1 temperature, and del Cp, this is the difference of molar heat capacity as constant pressure of the products and reactants, and T2 minus T1. And the case 2 is when this delta Cp depends on temperature. In that case, this one delta H2 equal to del H1 plus and del Cp taken within this integration, and whenever it is expressed in virial form an experiment, and then we have found this one. Alpha and beta, these are the difference of virial coefficients of these products and the reactants, and these are the constant for that reaction. And I can now set one problem for this case 1. For this reaction, carbon monoxide gas plus half oxygen gas giving you the carbon dioxide gas, and the standard enthalpy of this reaction at 298 Kelvin equal to minus 67.650 kilocalorie. We like to calculate the value at 373 Kelvin for this one, for the same reactions. For the same reaction, and given this Cp values, Cp naught of carbon monoxide gas is 6.97 calorie mole inverse Kelvin inverse, and Cp naught for oxygen, it is this one, and Cp naught for carbon dioxide and this one. These are all calorie mole inverse Kelvin inverse. It is the unit of this molar heat capacities. So this del Cp, according to this form, this minus this one will be equal to del Cp equal to minus Cp naught of carbon monoxide reactant, one stoichiometric coefficient, and in this case minus half stoichiometric coefficient, half into Cp naught of Cp naught. This is standard molar heat capacity at constant pressure, and for oxygen gas, and product Cp carbon dioxide, Cp naught carbon dioxide gas. And the values are here given. We are putting these values here, and it is, since it is the in calorie mole inverse Kelvin inverse, but this one is kilocalorie, so this is to be expressed in kilocalorie, means into 10 to the power minus 3. So this value comes up minus 1.5 into 10 to the power minus 3 kilocalorie and Kelvin inverse. If we put here this relation for the standard states, and this one equal, this one to be calculated, and this one already been given here, and this del Cp naught is minus 1.5 into 10 to the power minus 3 kilocalorie Kelvin inverse, and this one is 373 minus 298 Kelvin, and Kelvin inverse cancels, and it is all the kilocalorie. If we do this problem, this one putting here, and minus 1.5 into 10 to the power minus 3 into the difference is 75 kilocalorie. So the final result is this one. So the molar standard enthalpy of a reaction changes with the temperature, and when the temperature, at this temperature 298 Kelvin, this one, at this temperature 373, this one. So now I give you another problem for this case 2. Now I shall illustrate with one problem for this case 2. Del H2 equal to del H1 and plus T1 T2 integration del Cp dt. Del Cp is the, for the standard state del Cp naught, and this one equal to the summation of nu I Cpi naught. This is the standard constant pressure molar heat capacity difference between the product and reactant. Or you can say this del Cp equal to my summation of nu I Cpi naught. Here the standard enthalpy of formation of ammonia gas at 300 Kelvin is given, this kilocalorie mole inverse. That means 1 mole of, so the reaction will be like that. 1 mole of ammonia is formed in this gaseous state from its constituent elements, and half nitrogen gas plus 3/2 hydrogen gas, and this is 1 mole of ammonia is formed. And find the value at 1000 Kelvin, given the heat capacities values for this respective reacting components are given. Nitrogen, this one here calorie mole inverse Kelvin inverse, and this is the T. This is a function of T, this is also function of T, this is also function of T, and these are the values of the reactants and products. So del Cp naught, whenever we are going to calculate, then minus for this reactant minus half the stoichiometric coefficient half, and Cp naught of nitrogen gas minus for the reactant minus 3/2 stoichiometric coefficient of this hydrogen Cp naught hydrogen gas, and plus for this product and Cp naught of ammonia gas, and these values are given here. So putting the values minus half and this value and plus this value and minus 3/2 and this one, and for this Cp naught of ammonia and this value is given. Whenever we are going, these are in calorie mole inverse, Kelvin inverse. So if we like to make it a kilocalorie, as the enthalpy of formation, standard enthalpy of formation of ammonia is given in kilocalorie mole inverse, so it is multiplied by 10 to the power minus 3, and so it is kilocalorie mole inverse Kelvin inverse. If we do this one, the term independent of T, and this one, this term depends on T, and this is the value of delta Cp naught. And the relation is like this: del H naught 1000 Kelvin, this is to be calculated, and this one given del H naught 300 Kelvin given, plus del Cp dt, and the temperature is ranging from 300 to 1000 Kelvin. So it is given here, this value inserted here, plus 300 to 1000 Kelvin, minus this value and this one, and 10 to the power minus 3 and dt, and dt. So whenever we are doing this integration, this one minus 11.03 kilocalorie per mole, and minus here minus 7.435 into this here dt integration T2 minus T1 means 1000 minus 300, and in this case 7.4 divided by 2, and T dt integration T square by 2 here 2, and T square 10 to the power minus 6 here, and it is 10 to the power minus 3, and kilocalorie 10 to the power minus 3, so 10 to the power minus 6, 10 to the power minus 6 kilocalorie, and it is T2 square minus T1 square according to the formula I have developed. So whenever all the values are inserted, the exact value coming up minus 12.867 kilocalorie mole inverse, and this one could be simplified as the 1000 minus 1000 square minus 300 square. You can write 1000 plus 300 into 1000 minus 300, means A square minus B square equal to A plus B into A minus B. In this way you can do this calculations. So this is all about this Kirchhoff equation, which relates or provides the relation for the heat change of a reaction at this temperature T2 if the same is known in other temperature T1, provided Cp values of the reactants or products should be known to us. So this is all about this thermochemistry. By this lecture I have completed the total content of this thermochemistry, and my next class will be the second law of thermodynamics, and this one is very interesting and also complicated, and this is the challenge of all of us to realize this second law of thermodynamics completely or fully as much as we can. So thank you all. and please subscribe if you like this lecture.